So, in our last class we started flux and we talk about how to find the flux, what is the formula associated with the flux. So, the flux associated with any surface visualize there are electric field lines and we have taken imaginary surface. So, like this. So, we define area as vector whose direction is perpendicular to the surface. For flat surface any direction you can assume positive, but if it is a part of closed surface then outward must be taken with positive sign. So, here I am considering this as area vector. For this surface and say this is the direction of electric field in space. If the angle between area vector and electric field, this angle is theta, then the flux passing through this element, flux passing through this small element, assume that this is dA, flux passing through this small element is given by E vector dot dA vector. That can also be written as magnitude of field and magnitude of area vector cos the angle between field and area vector, right. So, this is what we have seen in the last class and we solved one example based on this one. We calculated flux associated with this uniform field. So, flux associated with uniform field passing through any closed surface we got 0, right. So, no matter how the surface is, whether it is a sphere, cube, cone or anything which is placed in uniform field, the flux entering into it and the flux leaving it gets cancelled out. So, we have seen the flux associated with this surface and the flux associated with the back one, they were cancelling each other. Similarly, flux associated with this right one and the flux associated with this left surface, they got cancelled out and top and bottom cancel each other. So, total flux we got 0, but individually we got flux associated with all the surfaces, but the total flux associated with whole closed surface, in this case it is cube, came 0. Now, if field become non-uniform, same way I can proceed. So, the flux in the last class I considered this front one as first one and the back one will be second one, first, second, let this be third, this be fourth. So, fourth in front of this fourth one, this will become sixth one, and in front of this third one, this bottom I will call, let us call it fifth, then it will become sixth, right. So, third, this will become 4, this is 5, this will become 6. So, if I ask what is the flux associated with first surface, flux associated with first surface, let us write d phi is field, d phi field, that is 2xi plus 3j dot product with the area vector. On this surface if I take a small element, this is y direction and this is x direction, this is dy and this is dx, this area will be magnitude wise dy into dx, and as we considered outward positive, this will be the direction of area vector. So, I can write dy into dx I cap. Now, for this front one, everywhere x is changing, right. If you simplify this, then you will get 2x I dot I1, this will become 0, 2x dx dy, right. Now, for this one, height of this, if I consider this as A, this one A, this one A, the height of this one, this quantity is changing from 0 to A, while x is also changing from 0 to A. So, I can use double integration to integrate it, right. So, double integration d phi, one is for y, another is for x, will give me phi. So, here after double integration I will get phi, right, and limits for y it is 0 to A. So, let us first integrate y. So, when I integrate y, integrate this y, dy integration is y, upper limit minus lower limit, that will give you A. So, A I can take out, and then 0 to A I need to integrate, this will become x square by 2. So, 2 will get cancelled out, we will get A square by 2 got cancelled out, right. A square I am getting here. So, x square by 2 I will get, upper limit minus lower limit, only A square, this will give you A cube, right. Now, so as I go from here to here to here for this surface, x is changing, that change I have written here. So, this is the flux associated with first surface. Similarly, flux associated with second surface, the back one. So, for back one I will be writing minus I here. For back one I will be writing, I am talking about second surface which is behind this one, right. So, the back one I will write minus, and if I write minus, then I will get flux associated with second, directly I am writing same procedure, only thing minus I will come, this will become minus A cube, right. So, phi 1, phi 2 I have calculated. Now, similarly I can find out the value of flux associated with third and fourth. Let us see third and fourth. So, this I will clear. So, for third surface, if I take element somewhere here, then this is dx and this is dz. So, instead of writing dy, now I will be writing dz, and j cap will be the area unit vector. So, here I will write j cap and dz, dz, j cap, this is for third surface, right, third surface. If I do dot product, then j dot j will be 1, j dot I will be 0. So, here what you are going to get, this I will remove. Now, we are calculating phi 3, this I will write separately. So, phi 3, this is 3, you can see constant, and then dz and dx, and then again double integration. For x, integration is 0 to A, this edge length is A. So, to cover the whole surface from 0 to A you have to move. Similarly, to cover this one you have to move from 0 to A. So, for z also limit is 0 to A. This when you integrate, one A will come after integration of dx, and then another A will come after integration of dz. So, this will become 3A square, that is phi 3, right. So, I will write it separately, phi 3 we are getting 3A square, and phi 4 bottom one. So, see, for bottom one unit vector will be in this direction, as unit vector will be in this direction, here minus j cap will come. So, minus j cap when you multiply, this whole quantity will come as it is, but with minus sign. So, this will be minus 3A square. So, we are done with flux associated with first surface, second surface, third and fourth. Now, fifth and sixth are left. For fifth surface, for fifth surface, you can see, first I will remove this and this because it is not required now. So, area vector will be something like this and direction towards I cap, right. This is towards I cap, right. So, here I can write d z and dy, dz dy I cap, right. So, j over this is for fifth surface I cap, I dot I is 1. So, this will become 2 times x dz dy, I dot I is 1, I dot j is 0. Now, this I need to integrate, right. So, I have to place the limit of z and y because the value of x for this particular surface, value of x is a. So, here the value of x is a, here I will write a which is fixed. So, a I can take out, this will become 2a, and limit for z 0 to a, and limit for y is 0 to a. So, 0 to a, this is giving me a square, right. So, this will become 2a cube. Similarly, for this surface, if I talk about, now this was flux associated with fifth surface, right. Now, flux associated with sixth surface, separately I will write flux associated with sixth surface, that means this surface. For that you can see the value of x is 0. Every point on this surface will be having x 0 because it is yz plane. So, if it is 0, then whole term will become 0. Here x itself will become 0, this whole term will be 0. So, what we are getting 5 we are getting 2a cube, right. And phi 1 phi 2, what we did for phi 1 phi 2? So, for this surface it is dx dy outward k cap. So, I think I wrote for phi 1 I cap, actually it is outward is k cap. So, this is actually k cap, right, and the field is 2xi plus 3j dot E dot dA, right. For this one it is k cap. So, for phi 1 front surface, what is towards you is this. So, I dot I is 1, I dot j 0, I dot k 0. So, k dot I 0, k dot this one 0. So, this whole term is 0. So, flux associated with first surface 0, flux associated with second surface. For second surface I write the back one, I write minus k cap. So, minus will come here and this will become 0, right. So, this is what we are getting actually. So, phi 1 phi 2 we are getting 0 0, phi 3 phi 4 we are getting 3a square minus 3a square, and phi 6 phi 5 we have calculated. So, question is what is the total flux associated? Find the flux associated with the cube. Field is non-uniform, right. This is example of non-uniform field. So, when I add them all, phi is equal to phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6. You can see these two are 0 itself. This is 0 and this one is 0. Phi 3, phi 4 will cancel each other. So, these two will cancel each other, they will become 0. So, that means I need to just substitute the value of phi 5 and phi 6. Phi 5 is 2a cube and phi 6 is 0. So, this phi 6 is coming 0, this is coming 0 and this value is 2a cube. So, the flux associated with cube is 2a cube. I hope procedure is clear. For every phase I considered element because field was variable. Field is depending on x. As field was variable, for every element I calculated the flux associated with that and integrating will give me total flux. So, this is the way we can find out the flux associated if field is given non-uniform. You can see one thing over here, that if field is uniform, no matter what type of surface you have, the flux associated with a closed surface is always 0 if field is uniform. But if field is non-uniform, the flux associated may or may not be 0. So, in this case we are getting non-zero, but later we will see that field, if it is non-uniform, flux may be 0 also. How, that we will see later. So, I hope the application of flux formula is clear. Let us see another example. Let us take simple example. Visualize a hemisphere whose open surface is closed by a disc. So, here we have got one disc and this is a curved surface. Question is, what is the flux associated through hemisphere? So, just now I told if our field is uniform, then flux associated will be 0, right. So, total flux associated will definitely be 0. You can see there are two types of surfaces over here. This flat one, if I call surface 1, and this curved one if I call surface 2. So, for flat one, for this surface, area vector is defined in outward direction. So, the area vector here is like this is the area vector, but anywhere you take a small element over here, the area vector will be making different angles. So, here area vector will be like this. If I take element here, here area vector will be like this. D area, D area. But anywhere you take the element, you can see that area vector is making angle less than 90 degree. These all angles are less than 90 degree. That means for this one the flux associated will be positive, because everywhere area vector is making angle less than 90 degree. Cos less than 90 is positive. While you can see here field is in this direction, area vector in this direction, this angle is 180 degree, cos 180 degree minus 1. So, for this surface, so I can directly write the flux associated area that is nothing but pi r square into field magnitude I have written, then angle between them 180 degree. So, simplifying this one will give you flux entering into the hemisphere negative, minus sign indicate that flux is negative. Area vector is opposite to the direction of field. Now, for this curved surface, if I want to find out area, whatever getting in, that is only coming out. All the lines what are getting into the hemisphere, those lines are coming out of this curved surface. So whatever positive flux is negative flux is associated with this surface, same is the positive flux associated with this surface. So the flux associated with this curved surface is pi r square E. You can also get the flux associated by simple logic. Look at this one, lines will be this way coming out from the surface, right. If I allow light to fall, that will cast its shadow on vertical plane as circle. So I am allowing, forget about the field for time being, I am allowing light to fall. So on the vertical surface, if I take vertical surface somewhere here and I am allowing light to fall, this is light, then shadow will be something like this, a circle of radius r. So you can use the concept of projection. You can take the projection of this area, that is circle, and directly write field into area of projection pi r square, right. So by second logic also you can find out flux, or you can see directly from here number of line getting into the hemisphere and number of line coming out of the hemisphere, they are same. So whatever be the positive flux associated, same must be the negative flux associated. So whatever be the flux coming out through this surface, that must be equal to the flux getting into this one, right. Here it will be positive, here it will be negative, right. So what is the total flux? Total flux is 0. What goes in comes out, there is no net flux associated. So this is another example of uniform field where total flux associated with a closed surface is coming 0, right. Let us see another example. So instead of allowing line to get into the hemisphere this way, if I turn the hemisphere and then I ask, so this hemisphere is placed in uniform field, lines are getting into it. So you can see this line won't pass through, this line won't pass through, this line gets into the sphere, this line gets into the sphere. So these lines are getting into the sphere, hemisphere, and if I ask how much is the flux associated, so you can use the concept of projection. So if you are allowing light to fall, then allowing light to fall on vertical plane, the shape you are going to get of shadow will be something like this. So if the radius of hemisphere is r, this area will be pi r square by 2, half of the area of the circle, pi r square by 2, right. So you can visualize this situation as we have got imaginary area this way and lines are entering into it. So lines are entering into it, right. So how much is the flux associated? Flux in is minus area is pi r square E. Why minus? Because if you take element somewhere here, right. So this element will have area vector in this direction, dA vector, and the field at this particular point is in this direction. This is the direction of field. This angle, look at this angle, this is greater than 90. If theta is greater than 90, then d phi is equal to E dot dA, and this can be written mod E, mod dA cos angle. If this angle is greater than 90, this whole value will become negative. So all such element which is on this side will have the negative flux. You add all negative, what you will get? total negative flux. So lines are getting into this side surface, and whatever getting into, those will be coming out through this surface. So lines which are coming out through this surface, see. So all these lines which are getting into hemisphere coming out through this surface. If I take area vector here, if I take area vector somewhere here, if I take a small element and this is dA, you can see this angle, here angle is less than 90, right. So if angle is less than 90, cos less than 90, then this quantity will be positive. Every element on this side where lines are leaving, they will have positive flux. If you add all positive flux, you will get total flux positive. So flux leaving the sphere will be positive, pi r square by 2. This is area into field, So again same question, what is the total flux? What goes in comes out, so net flux is 0. So total flux associated is 0, right. Now let us see one more example. Now instead of hemisphere I have cone. So this way lines are getting into, and from this side it will be coming out. So this side flux will be negative and this side flux will be positive. Whatever negative flux we are going to get, same amount of positive flux we are going to get. So what is getting into? Flux in. So again I can use the concept of projection. If I allow light to fall on this cone and get the projection on vertical plane, then the projection will be a triangle. So projection of this one what is drawn in diagram will be something like this, a triangle. This distance is 2r radius, and let the height of cone be h. So this is 2r and the height of the triangle what we are going to get as shadow will be h. So what is the area of this shadow or area of the projection? So this area will be half base into height, half triangle, half base into height, base is 2r, height is h. So we are getting r into h as area. So if I ask what is the flux in, that will be field times, let field be E, field times this area. As it is in, area vector here will be in this direction, field lines making angle greater than 90 degree, minus sign will come, and E into RH will give you how much flux getting into it. How much flux coming out? Same amount plus E into R into H. Same logic. Through this lateral surface lines are entering into. So if I take area over this side of surface, you can see that area vector is making greater than 180. But if I take area somewhere here, then you can see here area vector is making greater than 90 degree angle, right, and here if you can see that area vector is making less than 90 degree. So dot product cos theta for all these small element and field combination is coming greater than 90 degree negative. For all these elements less than 90, positive. So, in is negative, out is positive, total is 0. So, we have just seen that irrespective of the shape of the closed surface, if it is placed in uniform field, the net flux associated, the net flux or total flux associated is always 0. So, we started with cube, then we took hemisphere, then we changed the orientation, and just now we have seen for cone also we are getting flux total 0, right. So, we have talked about uniform field, how to find out the flux through closed surface, right. Let us see another example. So, visualize imaginary ring, say at distance x. So, center of ring is at distance x, and say radius of ring is capital R. So, I have considered a ring whose radius is R. I hope diagram is clear. So, we have got a ring of radius R, and from center of ring at distance x I have placed a point charge. So, as you can see that out of all the lines originating from Q, few line will pass through ring. If I ask how much is the flux associated with the ring, then I can use the formula for flux. d phi is equal to field, area, and the cos of angle between area and field. Now, as the intensity of the field created by this charge at different point on the ring will be different, I can take a small element and integrate to calculate the total flux. If field is constant everywhere over the area, then I can directly write E dot A, provided field is uniform. But here you can see that everywhere field is different, that means field is non-uniform. If field is non-uniform, then I need to take element to get the flux associated with the element, and integrating that I will get the total flux associated. So, this is the procedure. So, how to take element, that is the question. Over this ring I can take imaginary strips. So, I can take strips like this and I will get the flux associated with this strip and integrate. You can visualize this ring is made up of imaginary strips. Get the flux associated with the strip and integrate, you will get the total flux associated with the area bounded by the ring, right. But the problem here is every element on this element won't be having same field. The condition here or the requirement here is this field must be same for every element or every element of the element. Here it will be different, here it will be different, here it will be different. So, I need to select the element in such a way so that at every point on the element the field is same. So, if you visualize element as ring instead of a strip, so if I take element this way, so visualize from charge you have imaginary ring. So, every element on the ring will be at same distance from the charge, the intensity of field produced by charge will be same if I take element like this, right. So, now I can easily write, so out of all the elements which are available, I found this element is more convenient to get the flux associated. Okay. Now, let us substitute the value. Area vector, let us start with the area vector. This element which is on this plane will have area vector exactly like this. So, here area vector will be this way, d area vector, but the field here is in this direction. You can see that if this line I can extend, it will be like this. If this angle is theta, this angle also be theta, and let the radius of ring be this ring is a small r, and this thickness of this one is dr. So, now we are ready to substitute the value. Field K Q divide by, here I want to find out field, this is x, this is small r, using Pythagoras I will get this under root r square plus x square. So, separation square means x square plus r square under root whole square, right, into area vector, because I have converted this whole expression in this format, I need to write the magnitude of area vector. Magnitude of area vector, area associated with this ring 2 pi r dr, right. 2 pi r is the periphery, and if you multiply periphery to thickness you will get area. So, 2 pi r dr into cos theta, this is theta, base upon hypotenuse, base x. So, base is x divided by hypotenuse under root x square plus r square. This I will simplify. So, to get total flux associated, I need to integrate this function. For whole surface of the disc, limit will be from 0 to capital R. So, this will be 0 to capital R. Now, what are the variable? The charge is kept at the fixed distance, x is constant. So, here this x is constant, this x is constant, only variable is radius, and for radius I have put the limit 0 to capital R. Let us take constant out and simplify. So, kq into 2 pi, x is constant, I can take x out. Okay, let us make this way. So, 2 I will keep with r. So, this will become 2r dr, and divide by, this will be x square plus r square to the power 3 by 2 integration 0 to r. So, starting itself in electrostat class 2, I told how to integrate such type of function, right. These are the standard function which are frequently coming. So, you need to remember the integration. Again I will tell, assume this one something, So, this will become t, and this will become dt, right. So, this is dt divided by t to the power 3 by 2. So, dt divided by t to the power 3 by 2. So, I assume this one, I am using substitution method to integrate this function. So, if I assume this as t, this numerator will become dt, integration of this one. So, this can be written t to the power minus 3 by 2 dt. If I integrate, this is t to the power plus 1 if I do, then this will become minus 1 by 2 and again minus 1 by 2 will come, right. So, this is coming minus 2 divided by under root t, and where t is what? T is x square plus r square. So, substituting this one here and then the value of t, I will get kq pi x 1 upon minus 2 divided by under root t, and t is x square plus r square. X square plus r square. Limit 0 to capital R. So, upper limit minus lower limit, take the minus sign out and simplify this, we are getting kq pi, get x inside, then this is coming in this format 1 minus x divided by under root x square plus r square. K and integration this 2 extra 2 that I write here. Now, k I can write 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught, pi and 2 will get cancelled out. So, you are left with q divided by 2 epsilon naught in bracket 1 minus x divided by under root x square plus r square. So, this is the flux associated with the area bounded by ring. So, you have placed ring in front of a charge. This charge was producing non-uniform field, the direction was different at different point and the magnitude was also different. So, what we did, we took a small element, in this case ring, and we got the flux associated with the small element, and after integrating for whole surface I get total flux associated. Now, I hope procedure is clear, result is important. So, let us analyze the result again. So, I will erase what is not required. See, we got flux passing through area bounded by ring is q upon 2 epsilon naught in bracket 1 minus x divided by under root x square plus r square. Again I am telling very important result, you have to remember this result, right, because we cannot afford solving the whole thing and getting the expression in the exam where time will be very limited for per question. So, we need to remember this one. You can easily remember the result. See, join charge to the topmost point, right, or I will join it this way. See, and let us call this angle phi. This is radius capital R, and this is the point where point charge is kept. So, look at this expression, x is base and hypotenuse is under root x square plus r square, right. So, I can write flux phi is equal to q upon 2 pi 2 epsilon naught 1 minus, do not get confused with this phi and that phi, better consider this as theta, okay, theta. Now, no confusion, I can write 1 minus cos theta. So, the flux associated with ring is given by q upon 2 epsilon naught 1 minus cos theta. So, if I say charge ring, this distance, let this be root 3 r and this is r, and I ask what is the flux associated. Only thing you require is this angle. So, what is this angle? 30 degree perpendicular upon base, r upon r root 3, 1 by root 3, 10, 30 degree. So, theta is coming 30 degree. So, if I ask how much is the flux associated, so substitute this value here, you will get the flux associated, right. So, flux associated for this situation is q upon 2 epsilon naught in bracket 1 minus cos 30 degree, only you have to substitute, cos 30 degree is root 3 by 2. So, that is the application of the formula, that for all such type of situation you can directly substitute the angle subtended. Be careful, this is not the total angle, right. If I join it here, this is not the total angle subtended, this is a semi angle you can say. So, from here if I visualize imaginary cone, this is semi angle you can say, right. So, flux associated with the ring depends on this angle and the formula is q upon 2 epsilon naught in bracket 1 minus cos theta. So, I hope by now you will be having idea how to calculate flux for different situations. Now, so before getting into Gauss law, let us consider some cases so that it will become very obvious what will be there in the Gauss law and your understanding will be more clear. So, if I place a charge outside a closed surface like in this situation, so visualize imaginary closed surface and charge is kept outside. So, if charge is kept outside, you can see the number of line entering into will be same as the number of line leaving. In the case of cone, in the case of hemisphere, we have seen what gets into comes out, but their field was uniform. Here I have taken the example of non-uniform field. Even field is non-uniform, the line getting into the surface from this side will be same as the number of line coming out of the surface on other side. So, these lines what you can see, they are contributing to negative flux, right. So, here this side if you calculate the flux associated due to the line getting into the surface, you will get the negative flux, and lines coming out, if this side you calculate flux, it will come positive. Again the same logic, here if you take area vector, if I take a small element over here, the area vector will be like this, and you can see field lines this way. If you extend this one, angle is coming greater than 90 degree, theta greater than 90 degree minus, right. But if you take element here, you can see that area vector is making angle less than 90 degree. So here flux associated is positive, here flux associated is negative. So whatever positive we are getting, same negative we are getting, so flux associated is coming 0. So flux through any closed surface due to outside charge is 0. This is the first point and the important one. So outside charge, due to outside charge, there won't be any flux associated with the closed surface, irrespective of the shape of the surface, cone, hollow sphere or hemisphere, cube, right, anything I place here, the net flux associated will be 0, important point. So first point is clear, I hope. Let us see second point. Before understanding second point, we have to understand the concept of solid angle. So concept of solid angle. So I already discussed solid angle in electrostat 3, right, where we calculated the flux, where we have calculated the field inside hollow sphere, uniformly charged hollow sphere. There I discussed the concept of solid angle. So here again I will tell. So if I take surface and I join all these contours to the center, this angle, look at this angle, this is called solid angle, and it is defined as the area of the surface, area divided by r square, right. So area divided by r square will give you solid angle. In this situation, every element are at the same distance, right. But if I have a element in such a way that all the points on the element are not at the same distance, like you can see here. So this diagram is something like so this point I have joined, and area is this way, you can see in the diagram. So area vector is in this direction, area vector in this direction, and if I join this to the center of the element, say this is making some angle theta. So here what I require is the projection of the area perpendicular to this r. So if I take element in such a way I am calling it ds dash, right. So the projection of this one this way I want to take, then this ds dash will be equal to ds cos theta. So solid angle if I want to write, then that is nothing but ds dash divided by r square, and this ds dash is ds cos theta divided by r square. you will understand the requirement later, but for time being we are clearing one concept of solid angle. So, I require the area which will be perpendicular to this R. So, I have taken the projection of this one in this direction. So, ds cos theta. So, ds cos theta will give you ds dash, right. So, this way I can write solid angle. Same thing here, this is theta, right. So, ds cos theta divided by r square will give you solid angle. I hope the concept is clear. So, how we are defining solid angle? Solid angle is ds cos theta divided by r square. How to use it? Later we will see, right. So, solid angle concept earlier we discussed, today also I told the definition. Now, we have just seen that when charge is placed outside the closed surface, there is no net flux associated with the closed surface. Lines are entering into and the same amount of line will be leaving the surface. So, flux associated was 0. Now, question is, what if the charge is inside the Gaussian surface, inside this imaginary surface? So, I will take the charge and place inside that imaginary surface, and now what would be the flux associated? See, so consider two surfaces. Let this be surface 2 and this be surface 1, okay. So, charge is there and visualize an imaginary surface S1 which is a sphere and charge is kept at the center. I ask how much is the flux associated with this one. So, through surface 1, so flux through surface 1 I want to find out. Procedure is, I will take a patch over here and electric field because of charge will be like this, and the area vector will be this way, d area vector. At every point on the sphere, if charge is kept at the center, area vector will be radially outward and field is also radially outward. So, the angle between these two will be 0, right. So, I can write mod E mod dA cos 0, right. If this I can integrate, I will get the total flux associated with S1. It's easy to find out because at every point on this imaginary one, first see S1 only, not S2, only S1. So, through S1 at every point field is same, that is k cube divided by radius of sphere is r square. Cos 0 is 1, right. So, this will be 1. Area dA I need to integrate, right. All these are constant, I can take out. Area I need to integrate. So, total surface area of the sphere is 4 pi r square. So, this integration will give me and if you simplify, k is 1 upon 4 pi epsilon naught, this r square gets cancelled out, q into 4 pi, this 4 pi gets cancelled out and you are getting q upon epsilon naught. So, charge is exactly at the center of a sphere and I found how much is the flux associated with the surface of the sphere. We are getting q upon epsilon naught. Now, instead of taking this spherical surface, if I take any potato shaped surface, any irregular surface like this S2, let us check whether we are getting same result or not. So, remember the result, q upon epsilon naught we got through S1. Now, S2, So, surface area is more, but the intensity of field at all the point on the surface will be less. So, let us see how the product will change, right. So, now focus on surface 2. So, I am interested in finding flux associated with surface 2. Flux associated with surface 2. So, on surface 2 I have taken this area, right. Formula we know, that is field, magnitude, area, magnitude, and the angle between them, cos whatever be the angle, right. Here area vector here in this direction and field is in this direction. So, this is the direction of area vector, right. This is the direction of area vector, dA vector, okay. So, if I draw another diagram for a better clarity, it will be something like this, right. So, this one is this area vector for this surface in this direction and field at that particular point will be along the line joining. So, this is the direction of field and the area vector here will be in this direction, right. So, area vector in this direction, field in this direction, here I light dA, here I light E and this cos phi. So, simplifying this one will give E dA cos theta, okay. And what is E over there at distance small r? So, from charge at distance small r, field is kq by small r square, right. So, I will substitute the value of field, E is equal to kq divided by r square dA cos theta, dA cos theta. Now, I will take this r inside and just now we have seen that this dA cos theta upon r square is solid angle, right. So, solid angle dA cos theta upon r square, right. So, this whole thing I can write solid angle, this whole thing I write solid angle, kq is left. Now, what is the angle subtended by the surface enclosing the charge at the charge? So, angle subtended in 3 dimension by this surface at the charge is 4 pi. Solid angle formula was d area divided by r square. So, if I take a sphere, look at this one, whether you take the sphere or you take any surface, the angle subtended at the charge will be same. So, for this surface if I calculate as it is coming same, anything which is covering the charge completely, they will subtend the same angle. So, here I write 4 pi r square divided by r square, I have written for this sphere, right. So, radius is capital R, let me write capital R. So, capital R square here, capital R square here, divide by capital R square, if it gets cancelled out. So, total solid angle subtended by the whole sphere at the center is coming 4 pi. Circle subtend 2 pi angle at the center. So, that is the linear angle, right, radian we write. This is solid angle. Its unit is steradian. So, this much steradian angle will be subtended by any surface covering the charge completely. So, in place of this total integration I can write 4 pi. So, I can substitute 4 pi over here, right. So, after substituting 4 pi, if I simplify, this 4 pi and 4 pi will get cancelled out and we are getting q upon epsilon naught, same result. So, if you have a charge and you cover it by any type of surface, it might be a sphere, it might be a cube, or it might be a cone, inside cone you are keeping charge, any surface which completely covers the charge, the flux associated through the surface is always q upon epsilon naught, right. So, charge is inside the closed surface, flux associated is q upon epsilon naught. Charge is outside, flux associated with the surface is 0. These 2 points we have to keep in mind, and these 2 points are the statement of Gauss law. See, so let us get into Gauss law. Okay, before getting, let us see. So, no matter how our surface is, the flux associated will be same. You can see through this one, if I draw line, these 3 lines passing through this surface are also passing through this surface. So, for this surface when I will be writing, let us call it S1 and this is S2. So, for S1 if I will be writing, then I will write field as KQ divided by R square field, then I multiply to the surface area 4 pi R square, procedure we have just seen. This is the flux associated with surface 1, and similarly flux associated with surface 2, KQ divided by the radius of this one is 2R. So, radius of this one is 2R, and the area of this one will be 4 pi 2R whole square. As this term is getting cancelled out, so irrespective of the radius of a sphere what you have selected, through all the sphere flux associated will be same, and what we are getting, K if you substitute 1 upon 4 pi epsilon naught, this 4 pi and 4 pi will get cancelled out, and again you have, and it has to be whatever line originating from this positive charge, they will go till infinity and they will also cross this outer one. So, all these lines crossing the inner one also passing through outer one. All those lines originating from the charge crossing the inner one, they are also crossing the outer one. So, the flux associated through this surface and this surface is bound to be same, and which is coming same, q upon epsilon naught, right. So, again the same statement, q cover the charge completely, the flux associated will always be q divided by epsilon naught. Now, I have kept few charge outside and few charge inside, and I ask how much is the flux associated. As you can see, from this charge line will be originating, and whatever getting in, those will be coming out. And there will be other lines which will not be passing through it, and they will be like this, right. So, the flux associated with this charge passing through this surface is 0, right, our first point. Similarly, flux associated with this charge, these lines will be entering into the surface and they will be leaving like this, and this will be leaving like this, right. This will be leaving like this. So, the flux associated, if I ask, flux associated through surface, this closed surface due to third is 0, flux associated with surface due to fourth 0. Now, look at first and second. So, through first lines will be originating, coming out, we have just seen, irrespective of the shape of this surface, the flux associated through surface as charge is enclosed, here, that is q 1 upon epsilon naught. As charge is positive, lines will be originating from charge and going till infinity, it will contribute to positive flux. What if our charge is negative, like we have here? So lines will be coming from infinity and terminating at this negative charge. So lines are coming from infinity and terminating at this negative charge. You can see that lines are getting into the surface, they will be contributing to negative flux. So these all lines which are terminating at Q2, they are contributing to negative flux. So if I ask what is the flux associated through surface due to second charge, it will come minus Q2 by epsilon naught. If plus charge is inside, then flux will be plus Q1 upon epsilon naught. If negative charge is inside, it will be charge divided by epsilon naught, where charge will be with sign, right. So if I ask what is the total flux associated with surface, so these two contribution will be 0, their contribution is 0. Now what is the total flux or net flux? Flux net, add these two, scalar quantity. So adding these two giving me Q1 plus minus Q2 divided by epsilon naught. So this is the combination of 2 points we have discussed. There is no flux associated with charge outside the imaginary surface. Flux associated will be only due to charge inside the imaginary surface, right. So I hope these 2 points in combination clear. Now let us see Gauss law. So Gauss law, what is the statement of Gauss law? It says that surface integral of electric field intensity over any closed hypothetical surface, we name that hypothetical surface as Gaussian surface, right, it is called Gaussian surface. So any imaginary surface is called Gaussian surface, right. So statement is closed surface integral of electric field over Gaussian surface is charge enclosed times 1 upon epsilon naught, right. So the surface integral of electric field intensity over any closed hypothetical surface in free space is 1 by epsilon naught times the net charge enclosed within the surface, and this is what we have seen, right. So this is actually closed line integral, circle, this represents close surface integral, close, we are integrating over the surface. So close surface integral of electric field. I hope this statement every term is clear. Close surface integral of electric field is 1 upon epsilon naught times the charge enclosed Q inside, and this is what we have just seen. In the previous case I told you that these two are not going to contribute to the flux, only these two are going to contribute. So if I ask what is the flux associated, what you will write? Flux associated will be 1 upon epsilon naught times charge enclosed by surface, q1 plus charge with sign, scalar quantity we are dealing, right. So 1 upon epsilon naught times the charge enclosed by the surface is the statement of Gauss law. I hope it is clear. Closed surface integral of electric field. What is this? So you take any point, say somewhere here, somewhere here I am taking element and say element is dA, right. So this dA is this one. Now this Q3 will produce field, here E3, and this Q4 will produce field here, that is E4. Look at this negative charge will produce field at this point towards the charge, that is E2. I have considered in this direction because charge is negative, right. And this one, this positive charge will produce field here in this direction, E1. So due to all the charges, you write the field, net field at this particular point and integrate over the surface, then the value of that integration comes q enclosed by epsilon naught, right. So that means this field is the net field, which is because of first one, second one, third one and fourth one. So this is the net field, right. So do remember that this is net field. So field on the surface will be because of all the charges, whether they are inside or they are outside. But when you integrate over the surface integral due to outside charge will give you 0, because that is representing flux and that was our first point. So similarly this outside one Q4 field you write on the surface and integrate for whole surface, you will get 0. I hope you are understanding. I will erase this one. What I am saying that this is representing the net field, whether it is due to outside charge or inside charge, we have to write net field over here. Now what I am saying, as this is net field, this is E1 vector plus E2 vector plus E3 vector according to diagram I am writing, E1, E2, E3, E4 dot surface area is equal to enclosed Q1 in this case and Q2 divided by epsilon naught. This is Gauss law, right. And what I am saying is there is nothing new. If you open the bracket, then you will get E1 dot dA close plus E2 dot dA close plus E3 dot dA close, and the last one plus E4 dot dA close. This is representing what? The flux due to first charge field into area over closed surface. This will give you Q1 by epsilon naught. So this is nothing but Q1 divided by epsilon naught. Look at this one. This will give you negative flux. So it will give you minus Q2 divided by epsilon naught. The third one, because of this one, flux associated, we have seen first point 0. So this is 0 and this is 0. So after simplifying this one, what we are getting? Q1 minus Q2 divided by epsilon naught, and this is the statement of Gauss law. So I hope analytically Gauss law is clear, right. So, assignment is uploaded on Gauss law, right. You can start solving the assignment and post your doubt if you have any doubt in the Gauss law. So, in next class we will talk about the application of Gauss law. So, I hope you enjoyed the class. Thanks for watching.